to introduce our next guest, Steen Rasmussen. When you look on the internet for Steen, you find an architecture professor at the MIT. You find a filmmaker known for his movie Russian Pizza Blues. You find a piano player. You find a dentist. You find a lot of Steen Rasmussens, but we have the real one coming from the Santa Fe Institute, and he will talk about, he's specialized in artificial intelligence, and he explores how living and intelligent technologies change society and what it means to be human. And last year we had people coming talking about transhumanism and how augmented technologies and augmented people are changing the way we are being defined as human. So we have the chance to ask Steen to explore this question with us. Welcome, Steen, and the floor is yours.
Thank you very much. So it's working, yeah. Yeah, thank you for letting me participate in this amazing event here. And congratulations with your new university and new airport. And gosh, it's a long time since I've been in Morocco. I'm really impressed. So I'm going to talk about engineering artificial living materials. And we're going to be in sort of technology readiness level 1, 2, maybe 3. So it's mainly basic science we are going to talk about. Many people have helped me along the way, sometimes been leading the way to try to understand how we can make living materials from non-living materials. And here is a long list of people, and I've sort of indicated as we go through the talk who's been doing what, but I also want to reach out to thank the sponsors, because to conduct research where we are trying to understand what the creative forces of nature is not so easy. Most funding agencies, they think it's kind of crazy, but we've been lucky and we've gotten quite a bit of money to do that. So I have a plan. I want to first try to answer why we should engineer artificial living materials, and then I'll try to outline how we can create life. And by doing that, we have to get into a little bit of technical details, because else it becomes hand-waving all of it, but I hope that you'll stay with me. And I promise there will only be a couple of slides that are a little bit technical. And then I'm going to try to explain what it is when we think about artificial living materials. And then, unfortunately, there are many details that we can't address here because we don't have that much time. And then I'm going to why is it blinking? Then I'm going to say a few words about the origins versus evolution. Turns out that evolution is not just evolution. There are things that one should think about. We have two modes of evolution. And finally, I'll talk about the implications. I mean, the day we actually can make artificial living materials, then what? And what does it mean for us? And there are two main reasons why I'm interested in it, and I think that these are sort of quite general. First of all, it's sort of a fundamental question I think most of us has asked ourselves: why are we here? What is life? Where do we come from? And what are these creative forces in nature? We all know that if we build a castle at the beach out of sand, it'll fall apart. We know that the mountains, they fall apart. So what is it in nature that enables really complicated things to grow and to develop like life and humans and all these societies and whatnot? But there's also another very important thing that has become much more important today than it was when I was a young man, when I started on this crazy journey here. Namely that I really believe that if we want to survive and be sustainable in a deep way, we have to figure out a way to adjust our technology so it becomes compatible with the living world. And this means that we have, all the way down to the material level, we have to make systems or materials that are completely compatible with the biosphere, so that when depleted technology can be used or can sort of circulate, the materials can circulate in the biosphere, and they can also be part of the other planetary cycle. So we imagine a future where pollution is not an issue anymore, because it is sort of a circular system a bit in the same way as we have in our natural ecosystems. So I think that's a very important issue. So as we're going to talk about living materials, I know that many of you think, okay, guys, what is life? And I have a definition where I say that there's not general consensus about that, but this has worked well for me. Life is a physical process that uses free energy to transform resources into building blocks that makes a system grow, divide, and evolve. And the growth and division is in part controlled by inheritable information that can change, so that selection and evolution is possible. It changes a little bit if you are looking at living processes on computers or computer networks or in robots, but we're not talking about that today. So I think this one is pretty good. Then there's a number of issues that my community, this artificial life community, is dealing with, and we're going to hit a few of them here in the next few minutes. So I conjecture that if we want to know how to build living materials, how to make this transition from non-living to living materials, we have to combine energy, materials, and information in a particular way. And does anybody know why it keeps shutting off? Does it also shut off there? It's maybe just these things here. So we need to start with a free energy gradient and catalytic reactions. So most of you probably remember from school, anyways, that chemical reactions they may or may not run, and you may make these chemical reactions run faster if you use catalysis. And catalytic compounds, they can speed up chemical reactions, some chemical reactions, whereas they don't speed up other chemical reactions. So this is where it all starts. And this is an idea that catalysis is essential for actually bridging non-living to living materials that many people have been advocating. Manfred Eigen and I don't know where Stuart Kaufmann is here today. He was certainly also one of the guys who have advocated that. So to actually argue, to give a physics argument for why that is, we have to consult Landau's principle. And there are two fundamental relations that we know from thermodynamics. One of them is Boltzmann equation. Those of you who are familiar with Boltzmann equation, you can smile and say yes. Else it says that there is a quantity that's called entropy that's related to how many states, microstates a system has. And then there is a relationship between energy and entropy. And it turns out that if you if you start with these fundamental discoveries or this fundamental knowledge we have from physics, then it turns out that if you want to delete a bit of information, or if you want to create information, it requires free energy. There's no way around it. It's physically impossible to create information or destroy information or maintain information without the availability of free energy. So if you want to create life, which is very much based on an ability to maintain information so that we can continue to exist and our bodies, they work, we must have access to free energy. And this is a fact that has never been, nobody has ever found anything to contradict it, so it's pretty safe to, if you want to make a bet on that. So we go back to this diagram, and we now have changed a little bit. So we say that this catalyst can actually take resources and turn them into building blocks if free energy is available. Now, if we take this a step further, then imagine that that one of these building blocks actually is a catalyst. Now we're getting someplace, because the more resources there are, the more resources can be turned into catalyst, which can convert the more resources into catalyst. So you have this, what's called a autocatalytic feedback loop. And I think this is a very important next step in our understanding. And it's not happening in every environment. That's why I've written the environment in. The environment is an important part. Now, imagine that these catalysts, you might be able to make catalysts with a little bit of difference in their constitution, or how they are composed, so that some catalyst works a little bit better to enhance this reaction, and some of them, they work a little bit worse. So there are these combinatorial catalysts that there is a possibility for selection. And if you further make the following assumption, and I know it's a little bit complicated, but please follow me, then you can actually, such a catalyst here, we know from chemistry and from biology that catalysts, they oftentimes are composed of more than one thing. And certainly there are many molecules that are able to act as energy transducers. These are molecules that can take one form of energy and turn it into another form of energy. It can either be like the ones we have in our bodies that will take the energy from when we eat peanut butter or bread or whatever, and then turn it into ATP that can then be used in our biosynthesis. But it can also be molecules like chlorophyll that can take light energy in, and turn it into to chemical energy that can then be used to generate the biomass of trees. So now the catalyst is composed of this energy transducer and this cofactor, and the cofactor influences the workings of this energy transducer. If it's a good cofactor, it'll run much faster, and if it is a bad one, it'll run slower. So in a way, you can think about such a system being hijacked by a cofactor that is better than all the other ones. And you can start to think about these cofactors as information. And that's exactly what we should do. So if we, besides a system that can generate catalysts for their own formation, also generates container molecules that can actually encapsulate, or in other ways create boundaries to the environment, then you are even better off, because then you can make sure that your energy transducer and your cofactor are co-located. And if they're co-located, then they work better. That's how everything is in chemistry, and I guess in physics too. The closer proximity you are, the better things they work, the more efficient their interactions are. And now you're pretty much there. Now you are ready to actually think about a living system. So if you have an appropriate metabolism, which is the energy transducer together with these cofactors, it also acts as a catalyst. Then you interpret this cofactor as information. You have that in a container, or you have it can be on the surface of an aggregate. And if you have that in an environment that's benign enough, so you have resources available, then you actually can generate minimal living processes. An interesting thing here is that you have both processes that are thermodynamically uphill. I mean, you have to take free energy to push the system to actually convert resources into building blocks, but then you also have processes that, so to say, are downhill, because once you have made these container molecules, they'll automatically assemble into structures that can then make sure that the energy transducer and the cofactor are in close proximity to each other. And the other thing that's really important to note is that when we have a living system, remember before, it has to grow and divide, it has to be able to undergo evolution. It's not that the growth sits anywhere here. It's not a particular molecule, and evolution is not a molecule. It's a process. So we generate life, we generate a living process from the interactions that such a system is able to produce. So here's another more artistic way of looking at it. This is the organizational structure of such a system here, where we are out on the right-hand side here, we take resources and light in, and the energy transduction makes sure that these resources are turned into either cofactor molecules or container molecules, and the cofactor then catalyzes, or it accelerates the process so that we have these things in a positive feedback. Further, the container is self-assembling, so it'll make sure that the cofactor and the energy transducer is in close proximity to each other. And this is Manfred Eichen and Ilya Prigozhin and von Neumann that in different ways have inspired us to think about a system like this one here. So once we've thought about the organization, I should say a couple of things more. I mean, how does it work, and which mechanisms are involved? So you should think about the energy transduction here from the right-hand side. It provides the free energy, or takes the free energy and converts the resources into building blocks. Then the cofactor, which you should think about information as information, modulates this process. So the better cofactor, the faster the metabolism, the more efficient the metabolism is. And there are two processes that are critical to actually make such a system work. And that is the cofactor's ability to act as a catalyst, and catalysis is usually associated, or all chemical processes are associated with some kind of dance with electrons. So in this situation, I will say that its ability to act as a charge transfer molecule. We're going to talk a little bit more about that. And then also, we need to ensure that this cofactor is able to replicate, because as the system grows and divides, you need to have more cofactor available so that the system can continue to work also as the daughter cells, they are there. So I haven't talked about materials, particular materials yet, and we've had many discussions about back in the old days how one should build such a system, and I've worked with many good chemists, and without them, of course, nothing would have happened. So we need to have some energy transducer molecules. We're using light, not because it's better, it's just that it's easier because it requires fewer components. We have a variety of different options for the container molecules. We're using simple fatty acid, decanoic acid, and actually I should say that we're using ruthenium complexes because it's one of the best known from chemistry, photochemistry. And then what kind of replicating cofactors we use? Well, we started out using peptide nucleic acid, PNA, turned out to be way too expensive to work with. I couldn't afford to have a protein synthesis lab, so we had to sort of divert and use DNA, because DNA is cheap and easy to work with. So we are using DNA as this replicating cofactor. And then there's one thing that you should think about, that we don't have a traditional design of our little protocell here. Usually you have the metabolism and the informational system inside a container. That's not how we do it. It's too complicated. We have a container, a two-dimensional container. We use the surface of the container so that we decorate the container on the outside with molecules that can capture light and molecules that are able to act as modulator on this energy transducer. So it's kind of important you think about, well, anyways, if you want to think more about this system, that you can actually design living systems that are different. This is much simpler, and I think that this is probably how how it happened. I'm not the one that knows about how things were about 4 billion years ago. I guess nobody knows, but it's certainly simpler to make such a system than a system that's modeled after a modern cell. Yeah, so can I show the movie? Because I think we should, that will much more easily explain what's going on. And then I can take a, so this is the story of the protocell. It's sort of an artistic interpretation for the chemist and a supermolecular chemist. That please don't be too offended. But we have here you can either think about it as an oil droplet that's decorated with fatty acid. It can also be a bilayer membrane, a vesicle. You have you have a double strand that comes in here. You have the ruthenium complex. And now we are feeding the protocell with picolinium ester. This is an oily substance. And as the protocell is sort of filled up and content, we cannot feed it too much because then it sort of disintegrates. Then we need to start replicating the cofactor. And that's happening here by providing some pieces of nucleic acid that then the system has to, our metabolism have to digest and glue together. So it doesn't work until we've had our system, our metabolism. Yep, light comes in, we glue these two guys together. So we have a duplex, we have a new plus and minus strand. And then we use the other light that comes in here to turn the oil into lipids, or to fatty acid. And as we turn more and more oil into, it's kind of a soap, then what happens is that this blob simply becomes unstable, and eventually it will divide. So it's not that we have any external forces that, or something from the outside that determines or that tells it to divide. We simply keep creating or turning oil into surfactant, and as we do that, then eventually something like this will happen here. And I hope we get, yes, so now we have 2 protocells. Thank you. Could we go back to the, yeah, here we go. So many other people or many groups across the world have come up with their own ideas for how, how one should think about sort of a minimal living system. And I think Gandhi was the first to actually propose such a system. I think we had our design in 2003. The most famous one is the one where you have an RNA that instead of doing electron transfer, you actually have the shape of an RNA acting as a ribosome. But anyways, there are many different ways one can imagine to make these things. And so far, none of us have really been able to create autonomous living systems. So now we come to the situation where we get into the details, and I can see my time is already running fast, but I just want to say one thing. We have a so-called ruthenium complex where we shine light on it, and we use the free energy from this ruthenium complex both to make the cofactors, new cofactors, and to make the container molecules. And if you are interested, you can of course visit, you can consult many of our publications. We've done comparative studies where we have both looked at the experiments, we've done modeling, computer simulations, and computations. This is actually a detailed view of the chemical reactions that our metabolism go through. The energy transducer you can see up there and the cofactor. And we haven't experimentally determined all the rate constant, but a number of them are determined. The rest of them we have sort of used computational methods to determine so that the whole system makes sense. And this was our first life cycle in the lab. This was Sarah Mauer's PhD thesis in 2011. And we've then done a number of experiments where we've shown that we indeed have budding, that we have inheritance of these systems by putting beads inside the vesicles. And we've shown that we can run both the cofactor generation and the fatty acid generation in parallel. And what we're stuck with right now is to make this cofactor replication at the interface. Other people have figured out how to make a replication without enzymes with a so-called leader process. I don't want to get into details with that. Here's what we are trying. We've anchored these DNA molecules on the surface. We haven't gotten high enough amplification. You can see these are after 5 generations, and it's not good enough yet. So it still requires work. And this is a so-called strategy to prevent the product inhibition, and this is Julia Gibbs-Gavis that came up with a way to do that. Other people have made self-replicating systems where the metabolism is, so to say, provided by the laboratory. This is one of Joy's systems from the 2009. And we've used AI systems to optimize the different reactions. And I don't want to get into details here, but just also show we have done experiments and calculations on how this charge transfer is happening. So I just want to, before I go finish here this scientific part, I want to say that I've changed my mind since I here the last couple of years, where I thought I was earlier of the opinion that there was sort of a gray area between what is living and what is non-living. And there were some people that said, no, you've got to come up with a definition, a crisp definition of what is life. And I actually think that maybe we can do that by looking at a system where you have right where the processes that, so to say, disintegrate our little protocell, when they are in balance with the processes that regenerate the protocell, that's sort of what I call self-maintenance. If the degradation processes are faster, then you have death. But then there is a place or a time where the cofactor, a new cofactor comes in, where actually you have that the self-maintaining becomes a little bit better. And at the place where you start to accumulate information, I think we might be able to define as a phase transition. And that should then give you a precise definition of when a system is alive or not. Well, since we haven't shown this experimentally yet, this is just a theoretical hypothesis. So then I just want to say that evolution, one could say that once you have evolution, once you have accumulation of information, then you should be golden. You can just evolve whatever you want. Turns out this is definitely not the case. There are 2 types of evolution. There's optimization, and then there's expansion. And for instance, these are experiments. I just want to show a single one where we have 50,000 generations of E. coli, which has been tested where you make a change in the food source, and then there is optimization of the system. And it turns out that this does not continue to invent. I mean, it's not the E. coli. They don't invent the wheel or the eyes or wings or something like that. It's very limited. So you have to add new things to generate new interactions to actually be able to make qualitative new discoveries. And if you take the logarithm, you can show that it's a straight line, and this is one of the hallmarks of this kind of evolution. So you have to go to data of human technology, or it can be economic development to actually test this with real data. And it's true, we do find 2 different types of evolution. There is this expansion, and there is the optimization. That's a long story. Just wanted to touch on it. And I want to finish up by talking about what the implications are. And of course, once humans are able to create artificial living materials, then we know how, at least one way of making this transition from non-living to living material. And we then have an idea of how the creative forces, they can be harnessed in nature. And maybe it'll sort of give us a little bit of guidance, a better understanding of why we are here, because it'll be easier to think about how we originally came here. But what's maybe more important here is that one thing that we must get away from is this upper way of running our societies. We take resources, we turn them into technology. As we dig out the resources, we make a lot of pollution. We make the technology, make a lot of pollution. We use the technology, make a lot of pollution, and we throw it away, and that also is pollution. We need to get into a situation where we have a living technology where there is a complete reuse of the resources, recycling, and that means that we should be able to disassemble all our technologies so that they can actually be used, materials can be used in a sustainable manner. Of course, we're not the one who invented that. Many people are talking about that, but very few people are talking about sustainability all the way down to the material level. Windmills pollute like crazy in the terms, once you have the used wind turbine wings, it's a big problem with waste. Once you're done with your photovoltaics, your solar farms, there's a big problem of actually separating these materials. So you still pollute with these things, and you need to find a way, or we need to find a way where you can actually completely regenerate it. So that way we can live in harmony with the planet instead of destroying our own existence. And that's why we need to change the way our economy works. That's what dictates how our institutions are organized. That's what dictates the upper one. But beneath all of that, we have to change our narratives, our understanding about who we are and what we do in our world. And a lot of that comes from, I come from a Christian country, it comes from the book of Genesis. And I think that it's very important that we start rethinking or reinterpreting what these great narratives they mean, because even though we are very special, we are still depending on this world we live in, and we should start to treat the world in that way, because the other ways or the way we're doing it right now is suicidal. Yeah, I don't want to talk about that here. So anyways, so this is a summary. I had the chance to argue for why we should engineer artificial living materials, also a little bit about how we make it, and then I talked a little bit about these two different ways we can view evolution, and then finally what it would mean if when we are able to generate these living materials. So I'll stop here and say thank you very much.